Hi everyone. Today we are going to talk about correlating financial time series with microblogging activity. And we are Bhavya Karki, Yu-Hsiang Lin, and Ziyi Zhong. So today we are going to talk about how can sentimental data leads to financial data and how to use interaction graph to represent information, which is a concept proposed in this paper, and their correlation results with the actual stock prices and also the trading volume. And also, we also tried. They also did a simulation which simulate the different trading strategy results, including incorporating the Twitter features into the trading strategy. And also, we were talking about several related works about this paper. So the objective of this paper is actually to find out what exactly is the Twitter feature that is most correlated with the change in your stock prices and the company of a specific company. And so by Twitter features, what they have in mind is actually about the countings. So for example, like the user number of users or the number of tweets. And the new idea they introduced in this paper is that they try to extract the relations among these fundamental countings into a graph representations. And we will talk about how this will improve the prediction ability of the model. And then about the stock prices, the stock properties, the measure they are talking about here is about the price change and also the trading volume. So the raw data, as you can see in the left-hand side of this slide, is really about, for example, if we extract all the Twitter posts about Apple company, and they will have a timestamps of each entry, and also there are different types of entries. Like this is the tweet ingredients. So here maybe the post user wrote in this tweet, and also there can be some hashtags, and also the user ID and the URL they are citing. So they may be talking about some specific news on the internet. So they will cite the URL. And so we transform this original raw tweets data into a graph representations. So in this graph representations, the center is actually a tweet post themselves. So it is actually really associated with the a tweet state. And since there is a tweet, there is actually some kind of retweet, which is like people cite the other people's tweets, but it is like presented as a form as another different tweet. So these authors actually perform some data engineering to relate these retweets together. And also there's a user who creates the tweets or the user that is being mentioned in the tweets. So these relations are connected by some edges. And then there are also some hashtags or URLs that are related to these tweets. So after having these graphs, we can construct a graph about this raw data. And so this is what the authors call as the constrained subgraph. And it is actually just about some specific tweets about a company within a time period, like T1, T2 is the begin and end of the time. And the construction of this graph is first you start with the tweets about this company within these timestamps. So these are the plus nodes. And then you add all the edges, which is connected to this major tweets. So these edges will connect to some users or other nodes, like the similarity nodes, which is they call as an implicit retweet, which means that you did not exactly cite the tweets, but the ingredients is essentially the same. And also the URLs. So by using these graph features, what we fundamentally introduced into the picture is that now the users' URLs or hashtags that are associated with the original tweets are included. And so this allows us to construct a different feature. So I think this is one of the major contributions of this paper. That is, they invented a way or proposed a way to do the feature engineering. So consider the fact that originally you only have, if you only count the raw data, like here, what they call the activity features, which is basically just a count with each types of nodes. And these are the features you can tell from the raw tweets data. So from these raw tweets data, what you can tell, for example, in this picture is that there are 4 nodes or 5 nodes that is about the tweets, and there are several authors. But if you are willing to go forward to construct a graph, then you can include the relationship information into this data representation. For example, here you will find that actually, although there are 4 tweets, but actually they are all about the same thing. Like they are basically just retweets of each other, and the user counts won't increase. They will just be connected to the same groups of tweets. And so one example is that so they propose a terminology which calls the graph features. So for example, you can count the connected components number. So here, all those 5 posts are actually belongs to the same connected components. So we are essentially remove the duplicates of the features. So you can think of like an analogy like MNIST data. If you want to judge or classify a handwritten digit images, originally you have a row pixel of 700 features in it, but eventually you can encode it as simple as the 4 binary digits for the 10 digits you possibly have. So it's like a feature encoding from the original data to some more representative data. So this can be just represent one big important properties of this Twitter post. So I guess this graph features, most importantly, they introduce this kind of extracting useful features from the raw data. So the author, they analyzed the correlation between the Twitter features and the traded volume and also the price of the company, of an individual company. And so they found that the strongest correlator to the traded volume as well as to the price is actually the number of connected components. But in the case of price, the correlation is actually much weaker. And they also found that if you, instead of using individual companies, if you group the top 20 companies together and then analyze the correlations, then you will find that although the number of connected components is still the strongest correlator to the volume, but in this case, it is getting much weaker than the previous case. And also, when you have more companies grouped together, we have a more reliable estimation to the other properties like page rank and the degree of nodes. So in this case, the correlator to the price change actually becomes the standard deviation and skewness of the degree of nodes. So here shows the simulation results. And in this figure, the light blue curve is the Dow Jones index, and which can be regarded as a true label or the true price value you observe every day. And the black curve is the profit made by using the number of strongest connected component as the Twitter feature that guided the trading strategy. And a benchmark we can look at is this random one. So it is the light green curve, and other colors of the curves is the profit made by other trading strategies. And we can see that actually the black curve, which uses the Twitter feature, is shown to be the only one that can keep all the positive profit during the whole simulation period. And we can also see that it's interesting to note the random one is actually even doing better than other more sophisticated strategies. So which may indicate that in their paper, they might choose some weak benchmark to use. So this result may not be completely fair.
For a related study, I would like to give a little insights into how deep neural networks can be used for stock market analysis on financial news data. By news data, I don't just mean the stock price index, but also the general public opinion of the companies, the market, and the sentiment of the investor in the market. So the authors here obtained financial news data from about 106 million Reuters articles and about 450 million articles from Bloomberg. Let's now begin with the data pre-processing. So first they remove suffixes and prefixes from names of every company and store it in its colloquial form. For example, Microsoft Corporation is stored as Microsoft, and the suffix or prefix for companies with common words are not removed, just so that you can differentiate them. Then from the set of news articles are restored sentences that mention at least one public company. Then you group these sentences by publication date and the underlying stock name. So here's an example of how a company and its related features are stored. You have the publication date, the title, that is a key sentence that identifies the company on that publication date, and body. The body comprises of all sentences from the articles that have that particular company name. In addition, you have a positive or a negative tag associated with this entry. This suggests whether there was a price drop or a price raise at the end of the next day. The authors use a bag of keywords model to represent this document, just so that they don't take the redundant words into the algorithm. The keyword collection is an iterative process where you have a seed keyword and you keep collecting keywords that are related to that seed keyword. After that, they compute the term frequency and the inverse document frequency for this keyword vector. Further, calculate the pointwise mutual information between every keyword and its positive or negative label. The final polarity score is determined by the difference between the positive pointwise mutual information and the negative pointwise mutual information for that word. Multiply with the corresponding TF-IDF scores and generate the feature vector. So once this is done, the authors identified a set of 10 category tags for each feature. These category tags are general identifiers such as new product or whether the company was acquired by another company, say a price drop, whether it went bankrupt, and etc., and calculate a new polarity score in a similar fashion. Next, you train a deep neural network to learn the price and financial news features. The prediction results generated are compared with each other to explore the best combination of features for this learning method. Here are the experimental results. You get the you get your neural network to predict whether it's a positive or a negative category. The first table shows the experiments on different learning rates, and they found out that a learning rate of 0.005 gave the least error rate of 47.64%. Next, they kept the other parameters constant and experimented using different number of hidden layers. Each hidden layer contained 1024 hidden neurons. This parameter was kept constant. The number of hidden neurons was kept constant. And again, the minimal error rate obtained was constant at 47.64%. Next, they altered the batch size that they trained on, and again, they got this to be the constant error rate. Finally, they used a combination of feature vectors to minimize the error, and the best error rate achieved was 43.13% using a combination of the price vector, bag of keywords, polarity score, and category tag as the feature vectors. Another piece of work that I thought was quite interesting was by G. Stilo and P. Velarde, titled Efficient Temporal Mining of Microblock Text and its Application to Event Discovery. They introduce a method called symbolic aggregate approximation to discretize a temporal series of data. I thought we could apply this to our case of finding patterns in a financial time series. So basically, the underlying principle is that words with similar temporal behavior tend to be closely related. Given a time series, they discretize it into finite levels, do a regex learning, and then perform hierarchical clustering on them to identify related words. Going into details, a time series is reduced to an arbitrary length n that can be partitioned using the piecewise aggregate approximation dimensionality reduction method. Beta breakpoints are identified and applied to produce n equally sized areas under its normalized curve. The PAA is then transformed into a string of symbols where each symbol is an alphabet and it's represented in this format. So this is a normalized time series for the word rider. Beta is fixed at 0, and when the curve goes above the point, you assign the alphabet B. When it's below beta, you assign it the symbol A. So the SAX string for this term rider becomes AAAA, BAB, and AAA. You perform this SAX conversion for every keyword in your collection, and after the time series normalization for words like Ryder Cup, golf, Europe, they found that their SX strings matched even though their z-scores was not matching. So this could be extended for fetching word occurrences of companies and their related uh, stock index or any news related to the company and its stock change. For example, if we have, say, we want to find out the stock prediction for Microsoft, we could use SX strings for MS, FT, Microsoft Corporation, Bill Gates, Windows, Bing, and so on.
Okay, let's see some other related works. The first one we see in is using sentiment data in stock prediction. As we see, the main paper does not use sentiment data, and Boland and L use 6-dimensional sentiment data: calm, alert, sure, vital, kind, and happy, and use a fuzzy neural network to train the model. We use as a baseline method in further related work presentations. And there is a very interesting thing that can sentiment data lead financial data. Is there any theoretical backup? There it is. We are using information theory, mutual information, to justify the correlation between social media data and financial data. If we see in the figures, for some specific companies and for some specific fields, there is a slight correlation between financial data and social media data. Let's see another related work. It's called non-parametric and topic-based approach. What's new about this is use topic-based sentiment for stock prediction rather than sentiment for the whole tweet. It requires natural language understanding, though it's shallow. And what is called non-parametric is we does not know how many topics are there, and it's non-trivial for human to find out. So we use a clustering method using a Dirichlet process mixture. Let's see basically how it works. Use a CDPM to learn a set of topics by clustering, and during this process, the topic evolution is also learned. And then we link the prior topics and neighbor topics. For example, the topic of day 0 could be Catalonia declares its independence, and the second day, the topic could be evoluted to the Spanish military force occupies the Catalonian territory. And then we compute a sentiment score for each topics and get a time series of sentiment scores. And therefore we got, like, for each topic we have a time series, and then given this time series we use vector of regression to train the model and predict the stock market price. Let's see the result. The matrix used is binary. We only predict the price go up or down. It's not numeric. And as we see, the green line is CDPM model is performed better than the red line and blue line. The blue line is index, which means we use autoregression on the financial data index itself. And the raw, the red line, means refers to the Boland paper we have seen just earlier. And let's see another related work using sentiment frame to predict stock price, which requires deeper natural language processing, which parses the semantic frames rather than use bag of words vector model. And they use novel tree to represent the semantics. Let's see these two sentences. Oracle sued Google in August 2010, saying Google's Android mobile operating system infringes its copyrights and patents for the Java programming language, and Oracle has accused Google for violating its intellectual property rights to the Java programming languages. These two sentences basically mean the same thing and have very similar semantic meaning, but they have very different bag of word representation. So therefore, if we use a deeper NLP using FrameNet to train the semantics, we probably find a similarity between these two sentences. Let's see how it works. In these sentences, the important words are Oracle sued Google saying something. So we parse different trees using these words and then combine them to a complete parse tree and use the semantic tree as a feature to train the model. Let's see the results. The matrix used in this paper is called MCC. TP means true positive, TN is true negative, FP is false positive, FN is false negative, and MCC is considering both person recall and avoids bias due to data skew. And it's great for a binary classification, and also in this paper classification is also binary, it's not numeric. And we see in the result figure, we see semantic tree performs better than the bag-of-word model and other models. Okay, and let's wrap it up. In this presentation, we have seen in this very lucrative topic, there are several features which are new that could be correlated with financial data, which are graphical features, topic-based sentiment data, and the semantic trees. And we have also seen several methods we can use, which is unsupervised learning, neural networks, and symbolic aggregate approximation. But there is a question remaining. Do you find the result satisfying? Will you trust your money with these auto traders in this paper presents? So the scene we discuss, I want to discuss is matrix and evaluation. We've seen several matrices, and almost each paper use different matrices. And the first one is accuracy. It is binary classification, which is naive. We only predict the stock price to go up or went down, or it does not care about like it go up 10% or 1% or 50%. So therefore, it is less likely to be applied into the real market, and it does not consider recall. As the MCC improved a little bit, it takes recall into account, but it's still binary classification. In the main paper, we see use an auto trader, which mimic which hallucinate auto trader to participate in the financial market and see it wins money or lose money. It's not binary classification anymore. It really sees how it will perform in a real financial environment. But it is also naive. It only holds stock for one day, only buys like the top 10 stocks and nothing else. And personally, I think the most important thing is why compare to a random buyer. As we can see in the figure, it compares the model it trained and to the random buyer, a buyer who like randomly buys some stocks. What's the big deal of beating a random buyer? The intuitive idea is random buyer like always lose money. So why are we comparing the model with the random buyer? It's no big deal of beating the random buyer. So my personal opinion is like there is a long way to go to form an auto trading strategy from social media data. And that's it. That wraps up our presentation. Thank you.